Hello and welcome to this lesson on unconformities. This is the second lesson in our relative dating series. In the previous lesson, we looked at the basic laws and principles that are involved in the relative dating process. We learned about the law of superposition, the principle of original horizontality, the law of inclusions, and the principle of cross-cutting relationships. So now we're going to talk about unconformities. An unconformity is a break in the rock record produced by erosion and or non-deposition of rock units. There are three types that we'll be looking at. So a break in the rock record means that deposition stopped, rock formation stopped, and in some cases material was removed. So the rock record is a record or a history of the events that occurred in the Earth's past at that particular location. So if we look at the picture that's shown on the screen, here is a location where there is an unconformity. These layers below and these layers above are separated by a long period of time. That long period of time is a portion of the Earth's history in that location where no new material was added to this rock formation. In fact, some material was removed. Remember from the previous lesson, we talked about the principle of original horizontality, the principle that states that rock layers or sediments are deposited in essentially flat horizontal layers. Well, these layers below right here are definitely not flat and horizontal. They have been incredibly altered. They have been disturbed. They're no longer flat and horizontal. They have actually been folded into an anticline and folded into a syncline. And that's actually the next lesson. So you're going to have to wait on that information. But because they have been folded, there was also involved what's called uplift, where there was vertical displacement of the rock units. They were lifted well up above the level of the ocean so that the surface became eroded. And that's what this is right here. This is an erosion surface. This is a location in this rock formation where there was no longer any deposition and material had been removed. And then something happened again to cause deposition to renewed deposition, a period of time when material was deposited again. And that's illustrated by these layers that are flat and horizontal above the disturbed layers. All right, now there are three different types of unconformities. And in all cases, the rocks that are below the erosion surface are older than the rocks that are above the erosion surface. In some cases, the location of the erosion surface is very easy to identify, like this picture. Here, the erosion surface is this region of the photo, right here. These layers beneath it are no longer flat and horizontal. They have been tilted. You would expect that there had been more material that extended this way, and it is now gone. So it has been removed through the process of weathering and erosion. So the material that's below the erosion surface could be many hundreds or millions of years older than the material above the erosion surface. The Grand Canyon is a spectacular rock formation where there are several unconformities. There are unconformities in between flat horizontal layers. there are unconformities in tilted layers as well, and on top of tilted layers. And we will return to this diagram again. All right, so let's look at the three types of unconformities. The first one that we're going to look at is called a disconformity. Here, strata or rock layers on either side of the unconformity are parallel. So all of the layers are still flat and horizontal in relationship to each other. So here's our erosion surface. So sometime after this limestone layer was deposited, deposition stopped, and then material was removed by weathering and erosion. That's what this is. This is the erosion surface. And then deposition occurred again and deposited these two layers on top. Now, this top layer of shale is now currently being eroded. That is a land surface, and there's rivers and streams on the surface of it. So if in the future deposition would occur again and new material would be deposited on top of that, that would form another disconformity. Here's another picture of an example of a disconformity. This one is very easy to identify because what's separating the two layers of sedimentary rock is a section of ancient soil. And the ancient soil would help a geologist find that material much easier than if the soil was completely absent and you would have two layers of rock touching each other. So below the erosion surface, so because there's soil that is developed there, deposition was not occurring. At this point, the rock formation was being eroded, weathered and eroded away. It was exposed. It was no longer beneath the ocean, on the ocean floor. The rocks below the soil are marine shale. So that was definitely on the ocean floor. And then it was lifted up and it was eroded. Soil was developing on that surface. And then at some point, the region became covered with ocean water again. And that is evidenced by this marine limestone that formed on the ocean floor. So this erosional contact separates rocks that are much older than the rocks above it. Oftentimes, a disconformity is discovered by the presence of fossils. The fossils below the erosion surface are much older organisms than the fossils of the organisms above the erosion surface. It's very unusual that there is a soil layer that identifies the unconformity. And it is often this gap in the fossil record that tells or shows the scientists that there is in fact an unconformity of this nature, a disconformity. So here's a little animation that I put together to illustrate a disconformity. First, we have sand that's deposited and later cemented into sandstone. Next, there's clay deposited and later compacted into shale. A coral reef then thrives on top of the shale, and it is later compacted into limestone. The surface is uplifted above the ocean, and erosion occurs to the limestone, removing that top surface. Again, the ocean comes in, and mud is deposited on the limestone. And then our final layer is more sand deposited on top of the shale. That sand later is cemented into sandstone. So what we end up with is an erosion surface that exists between the limestone and shale. It is that erosion surface that identifies the disconformity. All right, the next one we're going to look at is a nonconformity. A nonconformity is similar to a disconformity, but the rock type beneath the erosion surface is either igneous or metamorphic. And the rock on top is typically sedimentary rock, although it could also be layers of lava as well. All right, so when there is igneous rock or metamorphic rock below an erosion surface, that typically identifies a very, very large separation in the time scale. That's because igneous rock and metamorphic rock is typically very deep in the crust compared to the sedimentary rocks. So if erosion occurs down to this igneous and metamorphic rock, that has exposed rock that is very, very old. So here is our unconformity, this layer right here, this boundary. This is the erosion surface. So our igneous or metamorphic rock is below that, and all of these are layered sedimentary rocks above it. So here's my homemade animation of a non-conformity. First, sand is deposited and later cemented into sandstone. Oh, I'm missing something. Oh, let's back up here. We're going to start up there. Magma cools into igneous rock, granite. Let's start over. The next thing that happens is weathering and erosion removes material, leaving rocks of granite on the surface. And then next, clay is deposited. That clay surrounds the granite fragments. That clay is then later compressed into shale. And then on top of the shale, we have a layer of sandstone. So here we have an erosion surface that exists between the granite and the shale. The granite is much, much older than the shale. The last unconformity is called an angular unconformity. Here there are tilted and folded or faulted rocks below the erosion surface, and on top of them are flat, horizontal sedimentary rocks. So the erosion surface is easy to see. It's easy to see, it's right here. It's easy to see for two reasons. One, the difference in the color of the rocks is obvious, but also the layers beneath the surface are tilted, and the rocks above are flat and horizontal. It is more obvious because the rocks below are tilted. This also generally represents a longer period of time because the rocks below formed flat and horizontally, and something occurred to tilt them. So first we have to have the formation of these thick layers of tilted rocks, and then we have to have the events that cause them to tilt. So something that would cause large-scale rocks like this to tilt upward would be tectonic forces or the collision of plates that would lift that up. All right, so here's my animation of an angular unconformity. This is in two stages. First, sand is deposited and later cemented into sandstone. Next, clay is deposited and later compacted into shale. And then a coral reef thrives and is later compacted into limestone. Notice how all the rock layers are flat and horizontal at this point. And then we go to part 2 of our animation, and all of those layers, the limestone, the shale, and the sandstone, are tilted. So that's 4. The region experiences mountain building, and the layers are tilted and eroded. So that's what this represents, the erosion of that surface. These layers would have extended up further. And then the region is submerged again. Sand is deposited and later compressed into sandstone. And then on top of that, we have clay deposited and later compressed into shale. So our erosion surface exists right here. It's easy to see because we have disturbed layers below and flat horizontal layers above. And this, our erosion surface, represents the location of our unconformity. This series of diagrams just illustrates the formation of an angular unconformity. We begin by deposition of several layers of sedimentary rock in an ocean environment. And then 2 plates collide, and they cause that region to uplift. You see that it has been lifted above the ocean floor, so it is no longer covered with ocean and deposition has stopped, and we have plants growing on the surface. The erosion of that surface is carried downward so that now we have tilted layers or beneath our erosion surface. And then this last diagram, we have deposition of new material on top of the tilted surface. So this erosion surface represents the angular unconformity. All right, I told you we get back to this Grand Canyon diagram, and we have several, actually each unconformity is represented in this diagram. So most of them up here are disconformities because these are erosion surfaces between flat horizontal layers of rock. So the layer below this disconformity is older than the layer above. And the way they would tell that is by looking at the fossils. So the fossils in the red wall limestone would be older than the fossils, much older than the fossils of the Sapai group above it. Down here is an angular unconformity. You can see that the layers are tilted below and they're flat and horizontal above. So that is an angular unconformity. And then all the way at the bottom, and that strip is going to come up. I just know it. This one right here, these are igneous and metamorphic rocks below, and these formed as flat horizontal layers, although they are now tilted. So that is a nonconformity because igneous and sedimentary, or igneous and metamorphic rock are below the erosion surface. This diagram is showing also several different types of unconformities. So we have here, this is igneous or metamorphic rock. This is probably metamorphic rock because of the pattern. And this is igneous rock here. So this actually is an intrusion, an igneous intrusion. But the surface here, we have a nonconformity because we have an erosion surface that's between our deep and older igneous rock, and on top of that is our sedimentary rock, flat horizontal layers. Here is another nonconformity. We have metamorphic rock below, and we have sedimentary rock above it. It would have formed flat and horizontally, although now it is tilted. It has been disturbed. This is an angular unconformity. We have tilted sedimentary rock layers below flat horizontal sedimentary rock layers. So this is an angular unconformity. The only thing I do not see in this diagram is a disconformity. I do not see a disconformity in this one. One other thing to note, this goes back to our first lesson. There are many dikes and sills in this diagram also. So this is a dike and this is a sill. This is a dike, this is a dike, and these are sills. These little things right here are sills as well. All right, the last thing I want to show you is some animations. So I'm going to pull up this here. And we'll take a look at an animation for each of the different types of unconformities. All right, we're going to start with the nonconformity. So remember, nonconformity has igneous rock or metamorphic rock on the bottom and sedimentary rock on the top. So what's happening here is erosion down to the igneous rock, and you can see that erosion has created some rocks on the surface. Then the area was covered with water and sedimentary rock formed on top of that, leaving behind inclusions of the igneous rock. Let's take a look at that again. Erosion down to the igneous rock, the formation of inclusions or rocks on the surface, which then become inclusions when sediments are deposited on top. So our erosion surface is right here. So that erosion surface identifies the location of the nonconformity. And we can use the law of inclusions to identify that as an erosion surface. And that would also tell us that the igneous rock on the bottom is older than the sedimentary rock above it. All right, the next one that I would like us to look at is a disconformity, and I'm having trouble finding it. I guess it's not in this. All right, let's go to the angular unconformity. In the angular unconformity, we have deposition that forms sedimentary layers in an ocean environment, and then there is uplift. So there's forces, compressional forces on both right and left, which causes it to fold. I'm going to run this again because my explanation took longer than it did to run this. Okay, so there's our layers, and then we have uplift, which raises it above the ocean, and then erosion wears the land down, and then the ocean comes back in and new layers are deposited on top. So our angular unconformity is identified by this erosion surface. And the way we know it's an angular unconformity is the layers underneath the erosion surface have been disturbed. They're no longer flat and horizontal. They're tilted. This has been uplifted into a fold, so the whole feature is called a fold. But if you just looked at the right or the left independently, they're tilted layers. So you can think of a tilted layer as a portion of a fold. And then when the material gets deposited on top, this erosion surface is then referred to as an angular unconformity. Let me see if I can find the disconformity one. Angular. See, all of these are animations. I do not see. I thought there was a disconformity, but I do not see it. Let me see here. Maybe it's in this. Angular disconformity, there it is. Okay, the disconformity, here we go. So we have flat horizontal layers of sediment that are deposited and then become sedimentary rock. Erosion removes some of those layers. Deposition occurs again in an ocean environment, and then we have more flat horizontal layers deposited on top of the much older ones. So this type of unconformity is much harder to identify because it's flat layers, erosion surface, more flat layers. So this is where they would use the fossils. There would be a huge gap in the age of the fossils, and that would identify it as a disconformity. All right, that's it for today's lesson. Thank you so much for joining us. And I will see you in the next lesson. Have a good day.